Good afternoon, class. Today we're talking about colligative properties in our unit on properties of solutions. So colligative properties are a bulk effect, and they have to do with the effect of having a bunch of solute in solution regardless of identity. So this has an effect on the vapor pressure, the boiling point, the freezing point, and osmotic pressure. So what we're going to do first is look at molarity. Molarity is of course defined as being moles per liter and is a concentration, but volume is temperature dependent. So this can actually change as you change temperature. As you increase the temperature of a environment, the solvent will get a higher vapor pressure, and that'll actually change the amount that's in the liquid phase, so volume is temperature dependent. Molarity is great for something where you have a constant temperature, but it is poor for calculations where temperature changes. Conversely, what we can use is something like mole fraction, chi of A. Chi of a substance. So the mole fraction of A, chi of A, is equal to the moles of A divided by the total moles that you have. So let's look at a calculation involving the mole fraction of ammonia in a solution that contains 0.850 grams of ammonia dissolved in 125 grams of water. So what we need here is moles of ammonia, NH3. The molecular weight can be calculated from the periodic table. Nitrogen has a molecular weight of 14.007 grams per mole, hydrogen 1.008 grams per mole, and there are 3 of those. Adding all of that together, you get 17.031 grams per mole. To calculate ammonia moles, we use the mass of ammonia multiplied by 1 over the molecular weight. So we end up having is 0.850 grams of ammonia times 1 mole of ammonia, which is equal to 17.031 grams of ammonia, and that comes out to be 0.0499 moles. Now intentionally, I use a number, a unit, and a substance every single time because when you're doing dimensional analysis, only a matching unit and substance can cancel with exactly that unit and substance. So here we have grams of ammonia canceling with grams of ammonia. Next, we need moles of water, H2O. The molecular weight, again from the periodic table, is 18.015 grams per mole. Water moles are calculated by 125 grams of water times 1 over the molecular weight, dividing by 18.015 grams. And that gives us 6.94 moles of H2O. We can now calculate the mole fraction of ammonia, which is equal to the number of moles of ammonia divided by the number of moles of ammonia plus the moles of water. And that comes out to be 7.14 times 10 to the negative 3. Similar to a percentage, mole fraction does not have any units. Moving on, we have molality, which is defined with a small m as opposed to the capital M you see with molarity. And that's equal to moles of solute divided by kilograms of solvent. So molality is useful because it is volume independent, and it is which means that it is temperature independent. Let's use an example of molality. So what is the molality of ammonia in a solution that contains 0.850 grams of ammonia dissolved in 125 grams of water? The same example as above. Our moles of ammonia from before are 0.0499 moles of ammonia. We now need the kilograms of water. We can take 125 grams of water and multiply by a conversion factor of 1 kilogram being equal to 1,000 grams. Another way of writing this is 10 to the negative third grams is equal to 1 gram. But I will always write the larger number going with the smaller unit so that we can always divide by our numbers without using scientific notation. So we're using the reciprocal rather. So 125 grams divided by 1,000 grams is equal to 0.125 kilograms of water. We can then calculate molality by taking the moles of ammonia divided by the kilograms of water, and we come out to 0.399 molal. So these units use only masses in molar amounts. They do not vary with temperature and are better suited for applications requiring temperature-independent concentrations. We could then move on to another example where we have the mole fraction and we are calculating the molality. So here we have the mole fraction of iodine, which is an iodine element bound to itself, dissolved in dichloromethane, CH232, Drawn here in a tetrahedral shape, it is very similar to chloroform as we drew last time, only with one less chlorine replaced by hydrogen. So it's CH2Cl2, and it is overall a polar molecule. So the mole fraction of iodine dissolved in dichloromethane is 0.155. We are looking now for the molal of iodine in this solution. So what we need are the moles of iodine in order to figure this out, because the chi of I2, the mole fraction, is going to be equal to the moles of iodine divided by the total moles. And we have that set equal to 0.155. So first, what we can do is impose a hypothetical 1 kilogram of solvent. Because this is a solution, it does not matter how much stuff we have, so we're going to impose 1 kilogram to make this whole molality portion of the problem much, much easier. So we can take 1 kilogram of our solvent, CHCl2, convert it to grams, so multiply by 1,000 grams divided by 1 kilogram, and then multiply it by 1 over the molecular weight of 84.93 grams per mole, again calculated from the periodic table, and that gives us moles of dichloromethane, 11.77, which is going to be required to calculate our total moles. So down here we have our mole fraction, 0.155, is equal to our moles of iodine divided by moles of dichloromethane plus moles of iodine. We just calculated what our moles of solvent, dichloromethane, are, shown here. And what we can do is multiply both sides of our equation by the denominator, so we bring this whole sequence down here up and multiply it by 0.155 or 0.115, and that's what we get here. Our total moles, 11.77 moles of dichloromethane plus our moles of iodine, all multiplied by our mole fraction, is going to be equal to our moles of iodine. And so when we distribute the mole fraction into this expression here, we get 1.35 plus 0.115 moles of I2 are equal to our moles of iodine. There is an implied coefficient of 1 here, so we can do is take 1 mole of I2, subtract 0.155 to get rid of this portion of the expression, and move that over to the right side, and what we end up with is 1.35 being equal to 0.885, which is, again, 1 minus 0.115, moles of I2. And we solve for our moles of iodine, and that is equal to 1.53. Earlier, we imposed a 1 kilogram of solvent amount, which is great because our molality is then equal to 1.53 moles per kilogram. Next, we're going to take a look at how an increased amount of solute affects the vapor pressure. As a reminder, vapor pressure looks something like this, where we have a liquid phase and above it some of the molecules in the gas phase. The molecules in the gas phase are hitting the walls of your container, creating a pressure. As you increase the amount of stuff shown in magenta here, that stuff, the solute, is going to get in the way of the liquid phase evaporating into the gas phase, and when things get in the way, you end up having less in the gas phase, and so your vapor pressure lowers. So as we go between liquid and gas back and forth, the more solute we add, the less gas phase you end up having, and the lower the vapor pressure. The relationship between vapor pressure and solution can be shown with this graph, and it's described by Raoult's law. So in magenta here on the left-hand side of the graph, we have 0 of component A and 100% of component B and a given vapor pressure. On the right-hand side, you have 100% pure A and 0 of component B. So if you have vapor pressure of A, shown on the right side, as you trickle in and start adding B, your vapor pressure starts lowering, and eventually you're half and half, and you keep adding more B, adding more B, adding more B, and you have run out of A and you're at 100% B, and you're at the vapor pressure of pure B. This expression down here shows how we can calculate a new vapor pressure of a compound A depending on the mole fraction of A. And mole fraction of A is going to change depending on how much B we have. So for example, in green, as you add more B, the vapor pressure of A is lowered, and that is because our mole fraction keeps changing. So we have the vapor pressure of A is equal to the mole fraction of A times the original vapor pressure of pure A. And in our last example for the day, we're going to show how the vapor pressure of a pure compound can change as you include more and more solute and change the mole fraction of solute. So a solution contains 5 grams of urea. So the molecular weight of urea can again be calculated from the periodic table. That is a non-volatile solute, and it is being dissolved in 0.1 kilograms of water. If the vapor pressure of pure water at room temperature is 23.7 torr, what is the new vapor pressure of the solution after the 5 grams of urea has been added? So what we first need to do is get all of this into moles, because what really matters for this problem is the mole fraction. So we have molecular weight of urea is going to be equal to 60.056 grams per mole, again from the periodic table. The moles of urea can be calculated by taking the grams of urea times 1 over the molecular weight. The grams of urea cancel with the grams of urea, and we end up with 0.0833 moles of urea. We then need to calculate the moles of water. We have 0.1 kilograms of water, which we then multiply by 1,000 grams per kilogram, so we isolate water as a mass in grams, and then we divide by the molecular weight, which is expressed in grams per mole, and we get 5.55 moles of water. We can now calculate the mole fraction of water. So the moles of water divided by the total moles, which is moles of water plus moles of urea. That's going to be equal to 5.55 moles, which we just calculated, divided by 5.55 plus 0.0833 moles of urea, which ends up being 0.986. So when we calculate what the new vapor pressure of water is after we have added urea and changed our mole fraction of water, how has that affected our original pressure of water? That is what this equation is describing. So 0.986, you can sort of think about it as being like 98.6% of the original pressure. So original pure pressure of water is 23.7 torr. We multiply that by our mole fraction and we get out 23.4 torr. If we were to look back and consider water, our compound A, and we're using the same equation, we're starting here when we have no solute added. That is our vapor pressure under normal conditions with that little 0. So here's our vapor pressure of water, and after we've added a little bit of urea, our mole fraction has dropped, and our vapor pressure has also dropped as solute has been incorporated. And that's the end of the lecture for today.